There is a moment, far beyond the reach of any spacecraft, when the light of a star passes through the atmosphere of another world. The planet itself may be too small to see. Its clouds cannot be photographed in the familiar sense. No camera resolves an ocean, a mountain range, or a horizon. From Earth, the entire system appears as a single point of light, steady enough to seem simple. But for a few hours, as the planet crosses in front of its star, a thin ring of atmosphere stands in the path of that light. Most of the starlight continues toward us unchanged. A small fraction enters the planet's air, traveling through layers of gas before escaping back into space. Along the way, atoms and molecules remove particular wavelengths. Water vapor leaves one pattern, carbon dioxide leaves another. Methane, sodium, potassium, and many other substances have their own arrangements of missing light. By the time the beam reaches a telescope, the atmosphere has written a faint chemical record into the spectrum of its star. That record is rarely obvious. It may be hidden inside changes so small that the planet must cross its star many times before the pattern becomes clear. Astronomers compare the star's light during the transit with its light before and after. They separate the spectrum into many colors, including infrared wavelengths the human eye cannot see. Then, they look for tiny differences that repeat. In this way, a distant atmosphere is not viewed as a picture, it is reconstructed from subtraction. The method is called transmission spectroscopy, though the name makes the process sound cleaner than it is. Starlight passes through more than an alien atmosphere. It also passes through the instruments that collect it. When observations are made from the ground, it travels through Earth's own air as well. The host star may be covered with spots, bright regions, or flares that alter the spectrum. Clouds and hazes on the planet can flatten chemical features, hiding the gases beneath them. What arrives at the detector is therefore not a simple message from another sky. It is several signals folded together. The work of reading it depends on patience, calibration, and uncertainty. A bump in a spectrum may suggest a molecule, but its meaning depends on temperature, pressure, cloud height, and the chemistry of the world as a whole. The same gas can be produced in different ways. A single observation may support several possible atmospheres, and yet from these narrow traces of light, real landscapes of weather begin to emerge. Astronomers can estimate whether an atmosphere is clear or veiled by haze. They can measure how heat is distributed between the side facing the star and the side turned away. In some large, intensely heated planets, they can trace winds that carry energy across the globe. They can study clouds made not only from water, but from minerals and metals that condense under unfamiliar temperatures. None of this requires traveling to the planet. It requires only that the planet move across its star, that the light continue outward, and that somewhere in the distance, an instrument be sensitive enough to notice what the atmosphere has taken away. Tonight, we will follow that light backward. From the spectrum recorded by a telescope, through the thin air of a distant world, toward the clouds, winds, temperatures, and chemistry that cannot yet be seen directly. The alien sky remains out of reach, its starlight does not. A spectrum begins when light is separated. To the eye, a star may look white, gold, or faintly red, but that apparent color is a blend of many wavelengths arriving together. When a prism, a grating, or a modern spectrograph spreads the light apart, the single point becomes a long band. Each position in that band corresponds to a different wavelength, and each wavelength carries a slightly different part of the story. The result is not a rainbow in the decorative sense, it is a measurement. Across the band are dark lines, bright features, broad slopes, and small variations in intensity. Some are created inside the star. Others come from gas between stars. A few may be introduced by Earth's atmosphere or by the instrument itself. When a planet passes in front of the star, another set of features may briefly join them. To understand why, it helps to move down to the scale of atoms. An atom cannot absorb just any amount of energy. Its electrons occupy specific energy levels, and they move between those levels only when they receive a matching amount. A photon carrying the right energy can be absorbed. A photon with slightly more or slightly less passed through. Because photon energy is linked to wavelength, each atom removes light at a particular set of wavelengths. Hydrogen has one pattern, sodium has another, potassium has another still. Molecules produce richer patterns because they can rotate and vibrate as well as change electronic states. Water vapor absorbs across several infrared regions. Carbon dioxide leaves strong bands of its own. Methane, ammonia, carbon monoxide, and other molecules each alter the spectrum in recognizable ways. These patterns are often called fingerprints, though the comparison is imperfect. A fingerprint is usually clear and fixed. Molecular features can overlap. Their strength changes with temperature and pressure. Clouds can conceal them. Several different combinations of gases may produce spectra that resemble one another. The atmosphere does not sign its name in one clean line. It leaves a layered impression. During a transit, starlight does not pass through the entire atmosphere equally. The central body of the planet blocks the star completely. Around that dark disk is a narrow annulus where light skims through the upper layers of air. At some wavelengths, the atmosphere is nearly transparent. The planet appears slightly smaller. At wavelengths absorbed by a gas, the atmosphere becomes opaque at a higher altitude. The planet appears slightly larger. No telescope sees this apparent size change as a visible edge expanding and contracting. The effect is inferred from how much starlight disappears. A deeper transit at one wavelength means the atmosphere has blocked more light there. A shallower transit at another wavelength means more light passed through. Across the spectrum, these changing transit depths form the outline of atmospheric absorption. For a large planet close to its star, the signal can be measurable. A swollen atmosphere may extend across thousands of kilometers, and the planet may cross its star often enough for repeated observations. This is one reason the earliest atmospheric studies focused on hot Jupiters. These worlds are large, massive, and close to their suns. Many complete an orbit in only a few days. Their upper atmospheres are heated to temperatures far above anything found in Earth's sky. Their scale heights, which describe how rapidly atmospheric pressure falls with altitude, can be large enough to strengthen the transmission signal. They are not the planets most like Earth. They are the planets whose atmospheres are easiest to hear through light. In the late 1990s and early 2000s, as transiting exoplanets became known, astronomers began trying to detect this atmospheric imprint. One of the first clear successes came from sodium, observed in the atmosphere of a hot Jupiter. The signal was small, but its meaning was large. For the first time, the atmosphere of a planet orbiting another star had been chemically probed through starlight. The planet was no longer only a mass, a radius, and an orbital period. It had air with measurable composition. From there, the field widened. Space telescopes avoided many of the complications introduced by Earth's atmosphere. Ground-based observatories improved their precision and developed methods for separating planetary signals from terrestrial ones. Spectrographs became more stable, detectors became more sensitive. Observations stretched farther into the infrared, where many important molecules leave strong features. Each improvement brought new possibilities, but it also revealed how difficult interpretation could be. A feature expected from water might appear weaker than predicted. That weakness could mean there was little water. It could also mean that high clouds blocked the deeper atmosphere where the feature would have grown stronger. A nearly flat spectrum might indicate a heavy atmosphere with a small scale height, or it might indicate haze made of tiny particles scattering light above the absorbing gases. Even a clear detection rarely stands alone. Scientists compare the observed spectrum with large families of atmospheric models. Each model proposes a combination of temperature, pressure, chemistry, clouds, and planetary structure. A statistical process then asks which combinations are most consistent with the data. This method is known as retrieval. The word suggests that the atmosphere is already hidden inside the spectrum, waiting to be taken out intact. In practice, retrieval is closer to narrowing a range of plausible worlds. One model may favor more water and higher clouds. Another may allow less water and a clearer atmosphere. The data place limits on both, but may not choose between them completely. As observations improve, the range can become smaller. More wavelengths help because different gases absorb in different regions. Repeated transits reduce random noise. Better knowledge of the star reduces uncertainty in the light source. Instruments working together can sometimes cover a broader spectrum than one instrument alone. The process is cumulative. A planet crosses its star. The telescope records the event. The spectrum is calibrated. The star is modeled. The instrument is modeled. The atmosphere is modeled. And gradually, from many layers of correction, the likely character of the sky begins to take shape. This is one of the unusual features of exoplanet science. The atmosphere is often understood before the surface is seen. Winds may be inferred on a world whose continents, if it has any, remain unresolved. Clouds may be detected above a planet that still appears only as a slight dimming of a star. The distance does not erase the atmosphere completely, it compresses it into light. And light, when divided carefully enough, can carry the structure of a sky across hundreds of trillions of kilometers. A transit tells us what happens when starlight passes through the edge of an atmosphere. But a planet does not always stand in front of its star. For most of its orbit, it moves beside the star, behind it, and back into view again. During those changing positions, the planet contributes light of its own. Some of that light is reflected from the star. Some is heat radiated by the planet itself. And when those faint signals are measured across an orbit, another kind of alien sky begins to emerge. Imagine a planet moving around its sun like a dark bead around a lamp. When the planet passes behind the star, its contribution disappears for a short time. The combined light of star and planet becomes slightly dimmer, not because the star has changed, but because the planet has been hidden. This event is called a secondary eclipse. The primary transit measures what the planet blocks as it crosses the face of the star. The secondary eclipse measures what is lost when the planet goes behind it. By comparing the system just before eclipse with the system during eclipse, astronomers can estimate the planet's own brightness. At visible wavelengths, that brightness may include reflected starlight. In the infrared, it can be dominated by thermal emission from the planet's day side. The difference is small. A hot Jupiter may shine strongly in infrared terms, yet its star is still far brighter. For smaller or cooler planets, the contrast becomes more severe. The telescope must measure the combined system with enough stability to notice a change that may be buried inside detector behavior, stellar variability, and the background glow of the instrument. But when the signal can be recovered, it opens a window that transmission spectroscopy does not. Transmission spectra probe the thin upper limb of an atmosphere where starlight travels through long slanting paths. Emission spectra sample the warm face of the planet itself. They carry information from deeper layers and reveal how temperature changes with altitude. This matters because an atmosphere is not only a list of gases, it is a vertical structure. Near the top, pressure is low and molecules are sparse. Deeper down, pressure rises. Clouds may form at certain levels. Heat may be trapped below one layer and released above another. The same molecule can produce an absorption feature in one atmosphere and an emission feature in another, depending on how temperature changes with height. On Earth, the lower atmosphere usually becomes colder with altitude until the stratosphere is reached. In some intensely irradiated exoplanets, upper layers may become hotter instead. This temperature inversion can alter the shape of an infrared spectrum, turning familiar bands into patterns that point toward a very different thermal arrangement. The spectrum becomes a profile of the atmosphere's depth. Not a complete profile, not a direct cross-section, but a constrained account of where radiation is absorbed, where it escapes, and which layers are warm enough to contribute. Then there is the rest of the orbit. As a close-in planet circles its star, different portions of its surface come into view. Before secondary eclipse, more of the heated day side is visible. After eclipse, the visible fraction decreases. Near transit, the cooler night side faces us. The total light changes through this cycle. That changing brightness is called a phase curve. The idea resembles the phases of the moon, but the measurement is far more delicate. the planet is not resolved as a disk. Astronomers observe the combined point of star and planet, then extract a repeating rise and fall synchronized with the orbit. From this curve, they can estimate the contrast between day and night. A planet with little atmospheric circulation may show a bright day side and a much cooler night side. Heat remains near the hemisphere that constantly faces the star. A planet with strong winds may transport energy around the globe. Its night side becomes warmer, and the difference between the two hemispheres is reduced. Many short-period planets are expected to be tidally locked, rotating once during each orbit, so that the same side continually faces the star. One hemisphere receives uninterrupted daylight. The other remains turned away. At first, this arrangement can sound motionless. It is not. The atmosphere is forced by a permanent imbalance. Gas heated on the day side expands and moves. Cooler material from the night side returns. Rotation bends these flows. Waves travel through the atmosphere. Jets may form near the equator. Clouds may gather where temperatures cross the threshold for condensation. The result can be a global circulation pattern, unlike anything familiar on Earth. Phase curves allow some of that motion to be inferred. The brightest point in a planet's orbit does not always occur at the moment when the full day side faces Earth. Sometimes the peak arrives early. That shift suggests the hottest region has been carried eastward from the point directly beneath the star. A strong eastward jet can move heated gas before it has time to cool. The planet's thermal glow reaches its maximum while the hottest region is still rotating into view. On other worlds, clouds may reflect more light on one side than the other. A visible light for phase curve can then trace where reflective cloud banks gather, even while infrared observations trace heat. Two curves from the same planet may describe different layers of its weather. One follows radiation escaping from deep in the atmosphere. Another follows starlight reflected by clouds high above it. Together, they offer a rough map made from brightness rather than pixels. This technique is sometimes called eclipse mapping or phase mapping. It does not produce a photograph. It cannot show a storm with a crisp boundary or a cloud deck with a recognizable shape. Instead, astronomers divide the planet into broad regions and ask which distribution of brightness best explains the changing signal. The answer may reveal that one hemisphere is hotter, that a hotspot is displaced, or that clouds are concentrated near a particular longitude. The planet remains a point, its weather does not. There is something almost familiar in the patience this requires. For most of human history, people learned the sky by watching repetition. The moon returned through its phases. Planets wandered and came back. Stars rose in their seasons. Meaning came not from one glance, but from patterns remembered across many nights. Exoplanet phase curves use instruments instead of memory, yet the principle is related. A single must return is not enough. The signal must return with the orbit. It must survive comparison. It must remain after stellar effects and instrumental behavior have been removed. Repetition gives the faint change a physical identity. The same is true for eclipses. A drop in brightness during one observation may be caused by the detector. A feature in one spectrum may be noise. But when the same planet disappears behind its star again, and the same loss of infrared light is measured, confidence begins to build. With enough observations, a world that cannot be seen directly acquires a daily rhythm. Its dayside warms, its atmosphere carries that heat. Its nightside releases some of it back into space. Clouds form where temperatures allow. Winds shift the brightest region away from noon. The planet moves behind the star, and for a few hours its light is gone, then it returns. This sequence gives astronomers more than composition. It gives behavior. It reveals whether an atmosphere holds heat or loses it quickly. It suggests whether winds are efficient. It may show whether clouds remain fixed, change over time, or migrate around the globe. In some cases, observations from different orbits do not match perfectly. That difference can be meaningful. It may suggest evolving cloud cover, variable weather, or changes in the star that still need to be separated from the planetary signal. Uncertainty remains part of the picture. A phase curve can often be explained by more than one atmospheric model. A small hotspot shift might come from weak winds, rapid cooling, magnetic effects, cloud patterns, or a combination of several processes. The data narrow the possibilities, but they do not always choose one. This is why atmosphere studies grow stronger when methods are combined. A transit spectrum describes the planet's limb. A secondary eclipse measures its day side. A phase curve follows changing brightness around the orbit. A high-resolution spectrum may detect gases moving toward or away from us, revealing winds through tiny Doppler shifts. A direct image, when possible, separates the planet's light from the star and allows its spectrum to be measured without waiting for an eclipse. Each method sees a different part of the same world. Together, they begin to form something more complete, not a surface map, not a photograph of an alien horizon, a climate reconstructed from light. Far away, on a planet bound closely to its star, there may be no sunrise and no sunset on the day side. The star may hang in nearly the same place, while air races beneath it and heat travels toward a night that never ends. No observer stands there to feel the wind. But the wind changes where the planet glows, and across the distance between stars, that changing glow can still be measured. The clearest atmospheric signal is not always the most revealing. Sometimes the spectrum arrives with deep, well-defined bands, and the gases can be traced with relative confidence. At other times, the expected features seem muted. The planet blocks nearly the same amount of starlight across a broad range of wavelengths, as though the atmosphere has covered its own chemical record. That flattening is often the work of clouds or haze. On Earth, clouds are familiar because water moves easily between vapor, liquid, and ice. Warm air rises, water condenses, droplets gather, ice crystals grow. Clouds form, change, and dissolve within systems shaped by temperature, pressure, terrain, and wind. On an exoplanet, the same physical principle applies, but the material does not have to be water. Any substance can form a cloud if the atmosphere becomes cool enough at the right pressure for that substance to condense. A world heated far beyond the boiling point of water may still have clouds, though they may be made from compounds that remain solid or liquid only under far hotter conditions. Some hot giant planets are expected to carry clouds containing silicate particles, the same broad class of material found in rock. Others may contain iron droplets, aluminum-bearing minerals, or salts. Cooler worlds may form clouds from sulfides, chlorides, water, ammonia, or other compounds, depending on the atmosphere and the depth being observed. The word cloud remains useful, but the image it creates can be misleading. These are not always pale banks suspended in a blue sky. They may be thin mineral veils high above a glowing atmosphere. They may form on the cooler night side, move toward the day side, and evaporate as temperatures rise. They may gather along one limb of a tidally locked planet while the opposite limb remains clearer. A cloud can be a weather event, a climate feature, and an observational barrier at the same time. During a transit, starlight skims through the planet's upper atmosphere. If an opaque cloud deck sits high enough, the light cannot reach the gases below it. Molecular absorption features that would otherwise deepen across the spectrum become shortened. The atmosphere may still contain water vapor, methane, or carbon dioxide beneath the clouds, but transmission spectroscopy sees only the region above the cloud top. The result is a spectrum with less structure. A high cloud deck can make a hydrogen-rich atmosphere resemble a heavier one. A haze can create a smooth slope that rises towards shorter wavelengths. Large particles can block light more evenly, producing a nearly gray opacity across a wide region of the spectrum. Several different skies can therefore leave similar traces. This is one reason a flat spectrum is not the same as no atmosphere. A small planet may possess a dense atmosphere whose features are hidden by clouds. It may have a heavy mixture of gases with a naturally small-scale height. Or it may have lost much of its air, leaving too little material to produce a strong signal. Distinguishing among these possibilities requires wider wavelength coverage, repeated observations, and careful modeling. Clouds complicate the view, but they are not merely obstacles. Their presence carries information. A cloud forms only where temperature and pressure allow a material to condense. If astronomers can identify the likely cloud species, they gain a clue about the atmosphere's thermal structure. If the cloud appears on one side of the planet but not the other, it can reveal how heat and winds are distributed. If cloud behavior changes over time, it may point toward active weather. Even when composition remains uncertain, the altitude of a cloud layer can affect the spectrum in measurable ways. A high cloud blocks a longer path through the absorbing gas below it. A lower cloud allows more of the atmosphere to remain visible. The spectrum may not show the cloud directly, but it shows where the atmosphere becomes opaque. Haze is related, though its origin can be different. Cloud particles usually form when a vapor condenses. Haze particles may be produced through chemical reactions initiated by light. Ultraviolet radiation from the star can break apart atmospheric molecules. The fragments recombine into larger compounds. Over time, these particles can accumulate into a high-altitude veil. A familiar example exists much closer to home. Titan, the largest moon of Saturn, is wrapped in an orange haze formed through photochemistry in its nitrogen and methane atmosphere. Sunlight drives reactions that build carbon-rich material. The haze obscures the surface in visible light and changes the way radiation moves through the atmosphere. Distant planets can develop their own photochemical layers, though the chemistry may differ from Titan's. Around small, active stars, ultraviolet and high-energy radiation can be especially important. It may alter methane, water, carbon dioxide, hydrogen sulfide, and other gases, producing particles that reshape the transmission spectrum. A haze can hide the molecules that created it, leaving only the broad effect of its opacity. The atmosphere becomes both the subject and the filter. Particle size matters. Very small particles scatter shorter wavelengths more efficiently than longer ones. This can produce a sloped spectrum, with the planet appearing larger in blue or near ultraviolet light. Larger particles scatter across a broader range more evenly, flattening the signal. The shape of the slope can help constrain the particles, but it rarely gives a complete answer by itself. Composition, size distribution, altitude, and atmospheric structure can imitate one another. The retrieval must account for many combinations, each capable of producing a similar curve. The problem becomes more complex because a planet's morning and evening edges may not be alike. During transit, starlight passes through both limbs of the atmosphere. One limb is rotating into daylight, the other is rotating toward night. On a tidally locked planet, these regions can have different temperatures, cloud cover, and chemistry. If the morning limb is cooler, clouds may condense there more easily. The evening limb, heated after a long passage through daylight, may remain clearer. When their signals are blended, a one-dimensional atmospheric model may describe neither side accurately. The spectrum is then an average of two different skies. More detailed models can allow separate temperature structures or cloud properties across the limbs. In some cases, observations during ingress and egress may help isolate them. As the planet begins to cross the star, one edge enters first. As it leaves, the opposite edge exits last. The effect is small, and the measurements are demanding. But the geometry contains a way to divide the atmosphere spatially, even when the planet itself cannot be resolved. Clouds also shape, phase, curves. A reflective cloud bank can brighten part of a planet in visible light. A thick night-side cloud layer may trap heat below it, while its top remains cool. Mineral clouds may form as gas moves away from the hottest region, then break apart when circulation carries them back towards stronger irradiation. This creates a moving boundary between condensation and evaporation. On some hot worlds, the temperature difference across the planet may be enough for the same material to exist as vapor on one side and particles on the other. The atmosphere transports matter through a planetary cycle, not of rain and rivers, but of rock-forming compounds carried by wind. The details depend strongly on altitude. Deep layers can hold different cloud species from upper layers because pressure changes the temperature at which condensation occurs. A planet may contain several cloud decks stacked above one another. Only the highest opaque layer may be visible in transmission, while infrared emission emerges from a different depth. The atmosphere does not have one surface. It has many effective surfaces, each defined by wavelength. At one wavelength, radiation may escape from high above the clouds. At another, it may come from deeper, warmer layers. A spectrum therefore samples several altitudes at once. By comparing them, astronomers can begin to infer where clouds sit and how sharply temperature changes below them. Similar cloud physics can also be studied in brown dwarfs. These objects do not sustain ordinary hydrogen fusion like stars, but many glow strongly in infrared light. Without the glare of a nearby host star, their atmospheres can reveal patchy clouds, vertical mixing, and changing weather. The comparison is not exact. An irradiated planet receives energy from a star, while an isolated brown dwarf cools mainly from within. Yet both can contain silicate, iron, and other condensate particles under conditions far removed from Earth's weather. These questions connect chemistry to climate. A cloud reflects some wavelengths, absorbs others, and changes where radiation is deposited. It can cool a planet by sending starlight back into space. It can warm lower layers by trapping outgoing infrared energy. The balance depends on particle properties, altitude, coverage, and the spectrum of the host star. Around a red dwarf, much of the incoming energy arrives at red and infrared wavelength. A cloud that reflects visible light efficiently may behave differently under that illumination than it would around a sun-like star. The color of the star becomes part of the climate system. So does the star's variability. Flares and changing ultraviolet output can alter photochemistry. Over long periods, this may change haze production. Stellar activity can also complicate the observation itself, because spots and bright regions on the star can mimic or distort slopes in the planet's transmission spectrum. A cloudy planet and a spotted star can leave overlapping signatures. The observer must model both. This is the recurring difficulty of alien atmospheres. Every layer of interpretation rests on another layer that must be understood. The telescope measures a change in light. The star contributes its own patterns. The planet's gases absorb. Clouds hide some regions, hazes scatter light. Instruments add small changes of their own. There is no single step where the distant sky becomes fully visible. Instead, confidence grows through consistency. A cloud interpretation becomes stronger when it explains the transmission spectrum, the emission spectrum, and the phase curve together. A proposed haze becomes more plausible when its particle behavior matches the star's radiation and the planet's chemistry. A thermal model gains value when it predicts where clouds should form and where the brightest region should appear. The atmosphere is assembled from agreements among many kinds of evidence. Far from Earth, a planet may be turning beneath a permanent sun. Along its cooler edge, vapor becomes particles. Winds carry those particles across the globe. Some fall into deeper layers. Some evaporate. Some remain aloft long enough to intercept a narrow beam of starlight. That beam crosses the system and reaches us years later. What it carries is not a picture of the cloud. It carries the cloud's refusal to let certain light pass through. Every atmospheric spectrum begins with a star. That may seem obvious. The planet does not create the beam used to study it. During a transit, the atmosphere is illuminated from behind, and the light source is the host star. But a star is not a blank lamp. Its surface is textured by magnetic fields, rising plasma, dark spots, bright regions, and patterns that change with rotation. Its ultraviolet output may vary. It may flare. It may send energetic particles through the planetary system. Even when it appears steady to the eye, its spectrum is alive with activity. Before astronomers can understand what a planet has done to starlight, they must understand the starlight itself. This is one of the central difficulties in the study of small exoplanets. Suppose a planet crosses a region of the star that looks uniform. The transit depth can be measured at many wavelengths, and differences may be attributed to the planet's atmosphere. Now suppose the star contains a large dark spot outside the path of the planet. The unocculted spot reduces the star's total brightness. The planet still blocks the same physical area, but against the dimmer star, the transit appears slightly deeper. Because spots have different temperatures from the surrounding surface, the effect changes with wavelength. a cool spot may influence blue light more strongly than infrared light. The altered transit depths can create a slope in the spectrum. That slope might resemble atmospheric scattering or haze. Nothing in the planet has changed. The star has changed the measurement. Bright magnetic regions, often called faculae, can create the opposite kind of distortion. Their contribution depends on wavelength, position on the stellar disk, and the geometry of the transit. A planet may also cross directly over a spot or bright region, producing bumps or irregularities in the transit light curve. Some of these crossings are visible in the data and can be modeled. Others are too small to identify individually. A star may contain many active regions below the resolution of any telescope, creating a surface that is heterogeneous even when the light curve looks smooth. The resulting effect is sometimes called stellar contamination. It is not contamination in the sense of dirt or damage. It is information from the star entering a measurement intended to describe the planet. The two are inseparable because the planet's atmosphere is observed only through stellar light. For large, hot planets around relatively quiet stars, the atmospheric signal can be strong enough that stellar effects are manageable. For rocky planets around small stars, the balance becomes more difficult. A small star offers an observational advantage. When a planet crosses it, the planet blocks a larger fraction of the stellar disk than it would in front of a larger Sun-like star. An Earth-sized planet may therefore produce a deeper transit around a red dwarf. The habitable zone is also closer to a cool, faint star, so a planet in that region completes its orbit more quickly. More transits can be observed within a shorter span of time. These advantages have made red dwarfs important targets. They are also magnetically active, especially when young. Some produce frequent flares. Their ultraviolet and X-ray radiation can vary sharply. Star spots may cover large portions of their surfaces. Their active regions can persist across many rotations, then shift or disappear. The same stars that make small planets easier to detect can make their atmospheres harder to interpret. This challenge grows because red dwarf systems are among the nearest places where astronomers can search for the atmospheres of temperate, rocky worlds. The planets are not bright enough to study easily. Their signals are small. A few parts per million in the measured transit depth may matter. At that level, the character of the star cannot be treated as background. Astronomers monitor stellar brightness before, during, and after transit. They observe at different wavelengths. They compare several transits across months or years. They model spots and faculae. They study spectral lines associated with magnetic activity. Even so, the surface of a distant star cannot be mapped completely. This creates a problem of degeneracy. A spectral feature might be explained by water vapor in the planet's atmosphere. It might also be influenced by cool regions on the star. A slope could indicate haze around the planet, or it could reflect the contrast between spotted and unspotted stellar surfaces. The solution is not to choose the more appealing explanation. It is to search for observations that separate them. Planetary atmospheric features should repeat according to the planet's orbit. Stellar features may change as the star rotates or as active regions evolve. A molecule may absorb in a set of related bands across the spectrum, while stellar contamination may produce a broader pattern. Observations outside transit help define the star. High-resolution spectroscopy can track activity indicators. Photometric monitoring can estimate the rotation period and the changing coverage of spots. No single method removes all uncertainty. Together, they narrow it. Flares add another layer. A flare begins when magnetic energy in the star's atmosphere is released. The star brightens, sometimes rapidly, across visible, ultraviolet, and X-ray wavelengths. The event may last minutes or hours. On active red dwarfs, smaller flares can occur often, while larger ones arrive less frequently. If a flare happens during a transit, it can distort the light curve directly. The affected data may need to be excluded or modeled, but flares matter beyond the observation. They interact with the planet itself. High-energy radiation can heat the upper atmosphere and break molecules apart. Over long periods, it may help drive atmospheric escape. especially on low-mass planets with weak gravity or limited magnetic protection. Energetic particles may alter chemistry and produce compounds that would not form under steady illumination. This does not mean that a planet around an active star must be airless. Atmospheric survival depends on many factors: planetary mass, gravity, magnetic environment, atmospheric composition, volcanic replenishment, orbital history, and the changing behavior of the star over time. A dense atmosphere may endure strong irradiation. A planet may lose light gases while retaining heavier ones. Chemical cycles may rebuild molecules after flares. The upper atmosphere may respond quickly while deeper layers remain buffered. The system must be considered as a history, not a single moment. A young red dwarf may spend a long time in a bright, active phase before settling. During that period, a planet now located in the habitable zone may have received much more energy than it receives today. Water vapor could have reached the upper atmosphere, where ultraviolet light separated hydrogen from oxygen. The lighter hydrogen could then escape into space. A planet observed in the present carries the result of that earlier era. Its current spectrum may reflect billions of years of loss, replenishment, cooling, and chemical change. The star is therefore not only the lamp behind the atmosphere, it is one of the forces that made the atmosphere what it is. This relationship appears in every planetary system, including our own. The young sun was more active than it is now. Solar radiation helped shape the upper atmospheres of Earth, Venus, and Mars. The planets responded differently because their gravity, composition, distance, magnetic fields, and internal histories were different. Mars lost much of its thicker, early atmosphere. Venus retained a massive carbon dioxide envelope. Earth maintained oceans and a nitrogen-rich atmosphere shaped by geology and life. One star did not produce one outcome. The planets answered it in different ways. Exoplanet systems may contain a wider range of answers. Some planets orbit so close to their stars that hydrogen streams away from them, creating extended envelopes detectable in ultraviolet or near-infrared light. Others may be stripped down to rocky cores after losing primordial atmospheres. Some may possess secondary atmospheres released by volcanism after the original gases have escaped. A measured atmosphere is therefore not merely a present layer of air. It is evidence of survival. When astronomers detect helium escaping from a planet, they can estimate how strongly the upper atmosphere is being heated. When hydrogen forms a cloud larger than the planet itself, the escaping gas reveals a world in transition. These observations help connect atmospheric chemistry with planetary evolution. A planet may begin with a thick envelope of hydrogen and helium gathered from the disk around its young star. If it is small and highly irradiated, much of that envelope may be lost. What remains could be a compact world with a heavier atmosphere or a bare surface exposed to space. Across large populations of planets, astronomers see patterns in size and orbit that may reflect this kind of atmospheric erosion. Individual worlds provide the detailed cases. The star supplies energy, the atmosphere absorbs part of it. Gravity holds some gases and releases others. Chemistry rearranges what remains. Geology may add new material from below. Time continues. This is why the atmosphere of a temperate rocky planet cannot be interpreted only as a collection of molecules. A molecule must be placed within the star's spectrum, the planet's gravity, the radiation environment, and the age of the system. Oxygen provides a useful example. On Earth, much of the atmospheric oxygen is linked to life. But oxygen can also accumulate without biology. Ultraviolet light can split water molecules. If hydrogen escapes more easily than oxygen, the remaining atmosphere may become oxygen-rich. The likelihood of that process depends partly on the host star. Methane can also be produced biologically or geologically. Carbon monoxide may offer context. Water, vapor, carbon dioxide, ozone, surface pressure, temperature, and stellar ultraviolet radiation all affect the interpretation. A gas gains meaning from its companions. The star is one of those. For generations, people treated stars as points used to measure direction and time. Their rising and setting divided seasons. Their positions helped travelers cross deserts and seas. The practical question was where a star appeared and when it would return. Modern astronomy asks more of the same light. A star's spectrum now becomes a record of temperature, composition, rotation, and magnetic behavior. Small changes once invisible to human observers are measured because they determine whether a feature belongs to a distant planet or to the surface behind it. The relationship has changed, but the reliance has not. The star remains the reference, only the precision has deepened. As telescopes gather more transits of small planets, stellar characterization will become part of every serious atmospheric claim. Observatories may watch the host star for long periods before combining its light with planetary models. Instruments at different wavelengths may work together, one measuring the transit while another tracks stellar activity. The planet and star will be studied as a connected system. This is slower than treating the star as a perfect lamp. It is also more truthful. A distant sky is shaped by the radiation above it. Its molecules respond to the color of the star. Its upper layers respond to flares. Its clouds reflect a particular spectrum. Its gases may survive or escape according to an energy history written over billions of years. And when the planet passes in front of that star, the atmosphere carries both stories at once. One belongs to the world, the other belongs to the light that formed it. The search for an atmosphere eventually reaches a more difficult question. Not only what gases are present, but why they are there. On Earth, the atmosphere has been altered by life for billions of years. Microbes, plants, animals, oceans, rocks, volcanoes, and sunlight all participate in a chemical system that never remains completely at rest. Some gases are produced. Molecules move between air, water, soil, and living cells. Seen from far away, Earth would not display forests, insects, or cities as separate objects. It would appear as a pale point beside the sun. Yet its spectrum would carry evidence that the planet is chemically active. This is the basis of the search for atmospheric biosignatures. A biosignature is not simply a gas associated with life on Earth. It is a feature that may be difficult to explain without biology after the planetary environment has been considered. The distinction matters because nature can produce many familiar molecules without living organisms. Oxygen is the best known example. On present-day Earth, most atmospheric oxygen is renewed by photosynthesis. Plants, algae, and certain microbes use sunlight to separate electrons from water and build organic matter, releasing oxygen as part of the process. Other reactions steadily remove that oxygen through respiration, decay, weathering, and combustion. Its continued presence reflects a long balance between sources and sinks. For this reason, oxygen in the atmosphere of another rocky planet would attract immediate attention. But oxygen alone would not settle the question of life. Ultraviolet light can break water vapor apart. Hydrogen, being light, may escape to space more easily, leaving oxygen behind. On a planet that once lost an ocean, a large oxygen atmosphere might remain after the surface had become dry. Light can also split carbon dioxide. Under some conditions, the resulting chemistry may allow oxygen or ozone to accumulate without biology. Whether this happens depends on the host star's spectrum, the abundance of water, volcanic gases, surface reactions, and the circulation of the atmosphere. An oxygen detection would therefore lead to more questions. Is there water? Is carbon monoxide present in unusual amounts? How active is the star in ultraviolet light? Does the planet appear to have suffered extensive atmospheric escape? Are there gases from volcanism that would normally consume free oxygen? The atmosphere must be read as a system. Methane presents a similar challenge. On Earth, much methane is produced by living organisms, especially microbes in oxygen-poor environments. It also comes from geological processes. Water reacting with certain rocks can produce hydrogen, which may participate in reactions that form methane. Volcanoes and hydrothermal systems may contribute smaller amounts. Impacts can alter atmospheric chemistry as well. A little methane is not enough. Its abundance, its lifetime, the planet's temperature, and the gases around it all matter. Methane is gradually destroyed by sunlight-driven chemistry. If a large amount were found in an atmosphere where it should disappear quickly, there would have to be an active source replenishing it. That source might be biological. It might also be geological. The task is to measure enough of the environment to estimate which sources are plausible. One promising idea is chemical disequilibrium. An atmosphere in equilibrium tends toward combinations of molecules that can coexist without reacting further. Life can push a planet away from that state by producing gases faster than natural reactions remove them. On modern Earth, oxygen and methane coexist even though they react over time. Both must be replenished. Their simultaneous presence has often been discussed as a possible biosignature, because maintaining the pair requires ongoing chemical activity. But even this comparison is not universal. The detectability of oxygen and methane depends on their concentration, cloud cover, the star's light, and the sensitivity of the telescope. Abiotic processes may create smaller or temporary imbalances, and a living planet does not have to resemble present-day Earth. For much of Earth's history, life existed without leaving a large atmospheric oxygen signal. The first organisms appeared long before oxygen became abundant in the air. Even after oxygen-producing photosynthesis evolved, reactions with dissolved iron, volcanic gases, and surface materials consumed much of what was released. A distant observer looking at the early Earth might have missed the biosphere entirely. This is a false negative. Life is present, but the expected sign is weak or absent. That possibility changes the emotional scale of the search. A world with no obvious oxygen may not be lifeless. Its biosphere could be small, buried, ocean-based, chemically unfamiliar, or simply living during a stage of planetary history when its influence on the atmosphere is difficult to detect. The spectrum records what reaches the air, not everything happening below it. There may be oceans under cloud layers, microbial ecosystems beneath soil, or biological cycles that produce gases too ancient for current instruments. A telescope can search only for signals that life, geology, and atmosphere allow to escape. For now, every proposed atmospheric biosignature remains potential evidence rather than a verdict. Scientists build frameworks that combine many kinds of information. The planet's mass and radius help constrain whether it is rocky or surrounded by a thick gas envelope. Its orbit indicates how much energy it receives. The host star defines the radiation that drives photochemistry. Other gases reveal volcanic activity, water loss, oxidation, or reducing conditions. Then the candidate biosignature is placed inside that setting. Ozone may support an oxygen interpretation because it forms from oxygen under ultraviolet light. Water vapor may indicate that the atmosphere has not been completely dried out. Carbon dioxide helps define climate and carbon chemistry. Carbon monoxide can provide clues about photochemical pathways and possible false positives. No one molecule is asked to carry the full meaning. The strongest case would come from several lines of evidence that agree, and from serious attempts to explain them without life. This caution is not reluctance, it is the method required by distance. A probe on Mars can examine rocks at close range. A spacecraft passing an icy moon can sample particles or measure local chemistry. For an exoplanet many light years away, the evidence may consist of few absorption bands within the combined light of a star and planet. The claim must remain proportional to the measurement. There is also a difference between habitability and habitation. A planet may orbit at a distance where liquid water could exist under suitable atmospheric conditions. That does not show that water is present, that the climate is stable, or that life began there. A detected atmosphere may contain water vapor without a surface ocean. A warm world may be habitable in one region and hostile in another. Habitability describes possibilities. A biosignature asks whether a process associated with life may already be operating. Astronomers may also search for changes through time. On Earth, biological activity varies with seasons, sunlight, ocean circulation, and the growth and decay of vegetation. A distant planet might show changes in surface reflectance or cloud behavior. Such a pattern would be difficult to measure. It would require stable observations over many orbits and careful separation from seasonal geology, changing clouds, and stellar variation. Yet time can provide context that a single spectrum cannot. A gas that rises and falls with the planet's seasons may reveal an active cycle. A surface color pattern that changes and returns could suggest chemistry tied to temperature or illumination. None would prove biology alone, but repeated behavior could strengthen a larger case. The search therefore moves slowly by design. First, a planet is detected, its size and mass are measured, its atmosphere is confirmed. Clouds and temperature stressed. The star is characterized. Several gases are identified. Abiotic explanations are tested. Only then does the possibility of life become scientifically durable. Many years may pass between those steps. Different telescopes may contribute different pieces. One generation may discover the planet, another may measure its atmosphere. A later observatory may obtain the spectrum that finally allows the difficult comparison between chemistry and biology. The same small point of light can remain in the sky through all of it. The instruments may change, and the people interpreting them may never meet. Yet each measurement can become part of a record carried forward, allowing a later observer to ask a more precise question than the one before. From the listener's present moment, the process may feel remote. Yet the light being studied is arriving now, one photon after another. It carries no label saying cloud, ocean, geology, or life. Those meanings are built carefully from patterns. This may be the most honest way to approach an alien sky, not by expecting it to resemble Earth, not by treating one molecule as an announcement, but by learning the planet well enough that its chemistry can be understood on its own terms. Somewhere, a distant atmosphere may be continually renewed by processes we have not yet identified. Its gases may remain out of balance, its seasons may alter the spectrum, its surface, if it has one, may exchange matter with the air. For now, all of that is held within a narrow band of starlight. The question of life begins there, not as a declaration, but as a pattern that refuses the simplest explanation. There is another way to read an alien atmosphere. Instead of waiting for a planet to cross its star, astronomers can try to separate the planet's own light from the glare beside it. This is direct imaging. The name suggests a photograph in the familiar sense, but the first images of distant planets are rarely more than small points. The planet may occupy a single cluster of pixels. No continent appears, no cloud front curls across a visible disk, yet that point contains light that has interacted with the planet itself. If the world is young and warm, much of the light may be infrared radiation escaping from its exterior. If it is cooler and closer to the conditions of Earth, the signal may be starlight reflected from clouds, atmosphere, ocean, rock, or ice. Once the planetary light has been isolated, it can be separated into a spectrum. The method no longer depends on a transit. The orbit does not need to pass directly across the star from our line of sight. The planet only needs to appear far enough from the stellar image for the telescope to distinguish the two signals. That requirement creates one of the most demanding contrast problems in astronomy. A planet resembling Jupiter can be millions of times fainter than a nearby sun-like star in visible light. An Earth-like world may be about 10 billion times fainter than its star. The planet also sits very close to that star in the sky. From many light years away, the distance between Earth and the Sun would appear as a tiny angle. Even a powerful telescope would see the two sources almost on top of each other. The planet's reflected light would be buried beneath diffraction, scattered light, optical imperfections, and the broad glow surrounding the star. The challenge is not simply collecting more photons, it is controlling where the stellar photons go. A telescope mirror does not focus a star into a perfect geometric point. Light behaves as a wave, and waves spread. The focused image is surrounded by rings and patterns created by diffraction. Small errors in the telescope's mirrors add speckles that can look like faint companions. A planet may hide inside one of those speckles. Worse, the speckles can change as the telescope shifts temperature, position, or alignment. A signal that seems planetary in one exposure may move or fade after the optical system changes. Direct imaging, therefore, begins with stability. The mirrors must be measured and adjusted with precision. The instrument must suppress the central starlight. The remaining pattern must be calibrated well enough that a faint point can be distinguished from the telescope's own behavior. One tool for this work is a coronagraph. A coronagraph places carefully designed masks and optical elements inside the telescope. These control the star's light before it reaches the detector, reducing the central glare and reshaping diffraction. The concept is related to placing a hand in front of the sun, though the engineering is much more refined. Blocking the visible disk is not enough. The surrounding diffraction must also be controlled. Modern coronagraphs use combinations of masks, mirrors, and wavefront correction. Small deformable mirrors can change shape by tiny amounts, cancelling parts of the unwanted light pattern. The aim is to create a dark region in the image where a planet may become detectable. This region is sometimes called a dark hole. It is not fully dark. Stellar light still remains, but within it, the contrast may become low enough for the planet's photons to stand apart. Another approach places the light-blocking system outside the telescope. A star shade is a large screen that would fly far in front of a space observatory, aligned precisely with the target star. Its shape would be designed to control diffraction as the starlight passes around its edges. From the telescope's position, the star shade would cast a deep shadow. The star would be suppressed before its light entered the telescope, while planets located slightly to the side would remain visible. The separation between telescope and shade would be measured across tens of thousands of kilometers. Both spacecraft would need to maintain alignment as they moved through space. For each new star, the shade would have to reposition. The journey between targets would take time and fuel, but the optical system inside the telescope could be simpler in some respects. A star shade could also allow observations across a broad range of wavelengths. Coronagraphs and star shades offer different strengths. A coronagraph remains attached to the observatory and can move between targets quickly. It demands exceptional control of the telescope's internal optics. A star shade separates the suppression system from the telescope, but requires formation flying over immense distances. Either method serves the same purpose. Remove enough of the star to reveal the planet beside it. Once separated, the planetary spectrum carries a different view of the atmosphere than a transit spectrum. During transit, starlight passes through a narrow ring around the planet's edge. With direct imaging, reflected light can emerge from the illuminated hemisphere. It interacts with a larger portion of the atmosphere and may carry information from the clouds and surface below. Oxygen absorbs visible and near-infrared light at characteristic wavelengths. Water vapor leaves several bands. Methane and carbon dioxide contribute their own features. The overall brightness can indicate how reflective the planet is. The color of the light can help distinguish a clear atmosphere from a cloudy one, though interpretation remains uncertain. Clouds can brighten a planet while hiding gases below them. A dark ocean may lower the average reflectivity. Ice and snow can increase it. Haze can alter the spectrum and change the apparent color. None of these components is likely to be resolved directly on a small, distant world. Their combined influence appears in the point of light. As the planet moves through its orbit, the visible illuminated fraction changes. Direct imaging can follow those phases without requiring a transit. The changing brightness may reveal how reflective material is distributed across the globe. A planet with broad cloud systems could vary as it rotates. A world with large differences between land and ocean might produce repeating color or brightness patterns, though clouds would complicate the signal. Seasonal changes could alter ice cover, atmospheric chemistry, or cloud behavior over longer periods. Extracting such patterns would require repeated observations with high precision. The rotation signal might be only a small variation inside an already faint planetary flux. Weather would change from one rotation to the next. The viewing geometry would shift through the orbit. Still, time offers information. A static spectrum describes an average world. A sequence begins to reveal a moving one. There may also be polarization. When light reflects from clouds, atmospheric particles, or a surface, its waves can become oriented in particular directions. Different materials and scattering processes produce different polarization patterns. Measuring this signal could help separate reflected planetary light from unpolarized stellar glare. It might also provide clues about clouds, haze, or a liquid surface. The interpretation would not be simple. Atmospheric scattering can mimic some surface effects, and the signal depends on phase angle. But polarization adds another layer that ordinary brightness does not contain. Direct imaging also allows planets on wider orbits to be studied. Transit surveys favor worlds that pass in front of their stars and close planets transit more often. Direct imaging favors angular separation, which can make wider orbits easier to resolve. The two approaches therefore explore different populations. Transits have revealed many planets close to their stars. Direct imaging has been especially successful with young giant worlds far from their suns, where the planets are still warm and bright in infrared light. The future aim is to move inward and downward in scale, toward cooler giants, toward smaller planets, toward rocky worlds receiving amounts of starlight that could permit temperate climates. Each step increases the contrast and reduces the number of available photons. A nearby Earth-like planet would not flood a detector. Its spectrum might be assembled from a modest stream of reflected light collected over many hours or days. Some wavelengths would contain more information than others. The telescope would need to remain stable while the planet moved against the residual stellar pattern. Background objects would need to be ruled out. Dust within the planetary system could scatter starlight and create a diffuse glow. This exozodiacal dust would resemble the dust in our own solar system that produces the zodiacal light. Around another star, a bright dust cloud could hide a small planet or add structure that complicates the image. The target system itself must therefore be understood. The star's brightness and activity matter. The amount of dust matters. The orientation of the planetary orbits matters. The distance from Earth matters. Even among nearby sun-like stars, some systems will be more favorable than others. Astronomers can prepare by measuring stellar positions, ages, activity, and possible debris disks. Radial velocity observations may identify planets before imaging begins. Astrometry can reveal the star's small motion across the sky as unseen worlds pull on it. These earlier measurements can predict where a planet will be. Direct imaging can then search a smaller region and return at later times to confirm orbital motion. No technique works alone. A radial velocity signal gives a minimum mass and orbital period. Astrometry adds the orbital inclination and true mass. Direct imaging measures the planet's light. Spectroscopy examines the atmosphere. Together, the methods transform a faint companion into a physical world. This layered approach may eventually allow comparisons among several rocky planets. One may have a thick carbon dioxide atmosphere, another may show little or no air, a third may contain water vapor and clouds, a fourth may display chemistry that resists a simple explanation. The value would not come only from finding one familiar planet. It would come from learning how varied rocky worlds can be when they orbit different stars and pass through different histories. Earth would become one atmosphere among many. For now, much of this work remains at the edge of present capability. The techniques are real. The early demonstrations exist. The giant planets already imaged are teaching astronomers how to suppress stars, calibrate speckles, and extract spectra from dim companions. Every observation improves the path towards smaller targets. Somewhere near a neighboring star, a rocky planet may already be reflecting light into space. The photons leave its clouds, cross the space between systems, and enter the solar system without announcement. Most pass unseen. A few may one day fall into a darkened telescope and remain after the star has been taken away. A single atmosphere can become a world of questions. A group of atmospheres can become a pattern. This is where the study of distant skies begins to change scale. The aim is no longer only to understand one planet in isolation, but to compare many worlds and ask why their atmospheres became different. Two planets may be close in size and receive similar amounts of starlight, yet one may hold a thick envelope of gas, while the other appears nearly bare. Two giant planets may have similar temperatures, but one is covered by high haze, and the other has a clearer atmosphere with deep molecular features. Two rocky worlds may orbit the same star. One may preserve water vapor, the other may have lost most of its lighter gases long ago. The differences become evidence. Planetary atmospheres are shaped by more than present temperature. They carry the influence of formation, gravity, radiation, impacts, geology, chemistry, and time. A spectrum observed today may contain the outcome of events that happened billions of years earlier. To read that spectrum fully, astronomers must place the planet inside its history. Some planets begin far from their stars, where the young planetary system is cold enough for ice and gas to accumulate. Later, gravitational interactions may move them inward. A giant planet that now circles its star every few days may have formed at a much greater distance. Its atmosphere may preserve traces of that birthplace. The relative amounts of carbon, oxygen, nitrogen, sulfur, and other elements can offer clues about where the planet collected its material. Different compounds freeze at different temperatures in a young planetary disk. A world forming on one side of a chemical boundary may acquire a different mixture from a world forming on the other. Migration then carries that composition into a new environment. The planet becomes a record of two locations. One is where it formed, the other is where it lives now. This record is not simple to recover. Atmospheric circulation can mix gases between layers. Clouds can hide important molecules. Chemical reactions alter the original material. Some elements may become locked deep inside the planet, beyond the region visible to a telescope. Still, population studies can reveal broad tendencies. Large surveys measure planetary radius, mass, orbital period, and the properties of the host star. Atmospheric observations add temperature, clouds, and composition for a smaller number of worlds. As the sample grows, astronomers can compare these measurements across many systems. Certain boundaries begin to appear. There are planets only slightly larger than Earth that may possess dense atmospheres. There are larger worlds with deep hydrogen-rich envelopes. Between them lies a range where some planets seem to have lost much of their original gas. This divide may reflect atmospheric escape. A young planet can begin with a light envelope gathered from the material surrounding its star. High-energy radiation heats the upper atmosphere. Gas expands. On a small planet with weak gravity, some of it escapes into space. Over time, the planet's radius shrinks. What remains may be a rocky core with a thinner secondary atmosphere produced by volcanoes, impacts, or chemical exchange with the interior. Other planets keep their primordial envelopes. Mass matters, distance from the star matters, the age and activity of the star matter. Even the planet's internal heat may matter, because it can help lift atmospheric gas toward altitudes where escape becomes easier. Across thousands of systems, these processes leave statistical marks. A pattern in planet sizes can become evidence for how atmospheres are gained and lost. The atmosphere of one world may remain uncertain. The population may still reveal the rules shaping it. This is a familiar movement in science. A single observation invites several explanations. A large collection begins to separate what is common from what is rare. The first known exoplanets seemed unlike the solar system because the easiest planets to detect were often large and close to their stars. As methods improved, smaller and more distant planets entered the catalogue. The apparent architecture of planetary systems became more varied. Atmospheres are following the same path. The earliest measurements favored inflated giant planets with strong signals. Then came smaller giants, warm Neptunes, sub-Neptunes, and a limited number of rocky worlds. Each new class requires greater precision and introduces different physical questions. A hot Jupiter may be studied through strong water absorption and a bright thermal phase curve. A temperate rocky planet may offer only a faint, nearly featureless transit spectrum. The lack of a strong feature is not a failure. It may indicate a compact atmosphere, high clouds, heavy gases, or no atmosphere at all. Each possibility describes a different planetary history. To distinguish them, astronomers can compare neighboring worlds in the same system. Planets orbiting one star share many conditions. They formed from related material. They have the same age. They receive radiation from the same stellar source, though in different amounts. This creates a natural experiment. If an inner planet appears airless while an outer planet retains an atmosphere, the contrast may reveal the effect of irradiation. If several planets have different densities, they may represent different stages of atmospheric loss. If two worlds with similar sizes show different chemistry, their internal histories may have separated early. Multi-planet systems allow the star to remain nearly constant while the planets change. That comparison can be more informative than studying unrelated planets around unrelated stars. The solar system offers its own version of this experiment. Venus, Earth, and Mars formed in the same broad region around the same sun. They are rocky worlds, yet their atmospheres are profoundly different. Venus holds a dense carbon dioxide atmosphere and a surface heated by a powerful greenhouse effect. Earth maintains liquid oceans and an atmosphere strongly influenced by geology and life. Mars has a thin carbon dioxide atmosphere and evidence that much of its earlier air and water were lost. No single variable explains all three: distance, size, interior activity, magnetic environment, water inventory, impacts, and long-term climate evolution all contributed. Exoplanet systems may provide many more versions of this comparison. Some may contain planets that began similarly and separated. Others may contain worlds that look similar today, but reached that state by different paths. This is why a spectrum cannot be interpreted only as chemistry. It is also biography. Carbon dioxide may reflect volcanism, atmospheric loss, ocean chemistry, or a stable climate cycle. Water vapor may come from an ocean, a steam atmosphere, high-altitude ice, or ongoing escape. Methane may be replenished by geology, biology, or reactions deep within a hydrogen-rich atmosphere. The same molecule can belong to several stories. A broader planetary context helps decide which story is plausible. Future atmospheric catalogues may therefore look less like lists of detected gases and more like families of worlds. There may be hot giants with mineral clouds and fast winds, warm sub-Neptunes with hydrogen-rich envelopes and deep chemical mixing, rocky planets with carbon dioxide atmospheres, dry worlds with residual oxygen, ocean-bearing planets hidden beneath clouds, bare planetary cores where the original atmosphere has been removed. Some categories may be common. Others may appear only under narrow conditions. The most valuable discoveries may not be the planets that resemble Earth most closely. They may be the planets that reveal a missing stage in atmospheric evolution. A world caught while losing its gas can show how a larger planet becomes a smaller one. A planet with an unexpectedly dense atmosphere can reveal how volcanic replenishment competes with stellar erosion. A system of several rocky systems lead to very different outcomes. The sky of each planet becomes one frame in a longer process. There is a generational quality to this work. The first observers who measured an exoplanet atmosphere could detect only a narrow chemical feature. Later instruments expanded the wavelength range. New methods began to measure temperature, winds, clouds, and escape. The next steps will come from telescopes designed with these questions in mind. Some observers will identify targets. Others will spend years refining stellar measurements. Another group may collect the spectrum. A later generation may reanalyze the same light with models that do not yet exist. The atmosphere will not change because the interpretation took time. Its photons will remain in the archive, waiting for better questions. This patience is built into astronomy. Light from a distant system may travel for decades before reaching a detector. Then, the measurement may be studied for years. A conclusion may remain uncertain until another instrument returns to the same planet. The scientific image grows by accumulation. One transit, one eclipse, one phase curve, one direct spectrum, one comparison with another world. Slowly, a population takes shape. From that population, astronomers may begin to understand which skies survive around active stars, which clouds dominate certain temperatures, which planets keep water, and which lose it before their systems grow old. No single planet can answer all of this, but each one contributes a small piece. Far away, millions of atmospheres are interacting with the light of their stars. Some are thick, some are thin, some are changing quickly. Others have remained stable for ages. Only a fraction will ever align for transit. Only a fraction will be bright enough for direct imaging. Only a fraction will be studied in detail. Yet even that limited sample can reveal the broader architecture of planetary air. One spectrum may describe a world. Many spectra may begin to describe how worlds become themselves. There is no final spectrum of a distant world. Every measurement is part of a longer sequence. A planet is observed with one instrument, then another. A feature first seen as a shallow bend may later divide into several molecular bands. A cloudy atmosphere that once seemed unreadable may become clearer at longer wavelengths. A world thought to be dry may reveal water higher in its atmosphere, or a planet expected to hold gas may turn out to be nearly bare. The picture changes because the light is measured more carefully. It also changes because the questions improve. At first, astronomers may ask whether an atmosphere exists at all. Then they ask what its broad composition might be. Later come questions about cloud altitude, temperature, circulation, escape, and chemical history. Each answer makes the planet less abstract. A transit becomes an atmospheric edge. An eclipse becomes a warm hemisphere. A phase curve becomes moving air. A spectrum, chemistry shaped by time. Still, the world itself remains distant. No current telescope can place an observer beneath those clouds. No instrument can feel the pressure at the surface of a small exoplanet or hear wind moving across unfamiliar ground. Even the most precise atmospheric measurements are interpretations of light gathered far from its source. That limitation does not make them unreal. It defines the kind of reality astronomy can reach. Most of the universe has always been known this way. Stars were understood from their spectra long before spacecraft approached one. Galaxies were studied through light that had traveled for millions of years. The composition of the sun was measured without entering it. Astronomy learns by receiving. A distant atmosphere is another form of that same practice. The photons arrive carrying the effects of temperature, molecules, particles, and motion. They do not explain themselves. They must be compared, calibrated, and placed within physical models. Some interpretations will change, some detections will weaken, others will become firmer as new observations agree. This uncertainty is not empty space around the knowledge. It is part of the knowledge. To say that water vapor is likely present is different from saying that an ocean exists. To say that methane has been detected is different from saying that life produced it. To say that a planet lies within a habitable zone is different from saying that it is inhabited. These distinctions preserve the value of the evidence. They allow a distant world to remain what the light supports, without forcing it into a familiar shape. The coming work will depend on time as much as technology. Small planets produce weak signals. Some will require many transits. Others may need observations spread across several orbital seasons. Directly imaged worlds may have to be revisited as they move around their stars, allowing their changing phases and spectra to be compared. A single night can begin the measurement. Years may be needed to understand it. That pace belongs naturally to the subject. Atmospheres themselves are products of long duration. Volcanoes release gases over geological eras. Stars alter their radiation as they age. Oceans exchange molecules with the air. Impacts remove some material and deliver more. Light gases escape, heavy gases remain. Chemistry responds to changing temperature and pressure. The sky above any planet is temporary on cosmic scales. Even Earth's atmosphere has not always looked as it does now. Its composition changed as the planet cooled. Oceans formed, rocks weathered, and life altered the chemistry. The air outside your window is one stage in a history that began before animals, forests, or breathable oxygen. An alien atmosphere will have its own sequence. It may be young and swollen with hydrogen. It may be thinning beneath strong stellar radiation. It may have reached a long-lived balance between geology and climate. It may be passing through a brief condition that will not last. When astronomers observe it, they see one moment from that larger story. The spectrum is a present tense, shaped by deep time. This is why comparisons among planets will matter so much. A single atmosphere may seem unusual, A group of similar worlds can reveal whether it is truly rare or simply unfamiliar. One system may show how distance from a star changes atmospheric survival. Another may show how planetary mass determines which gases remain. A third may reveal how clouds respond to a different stellar spectrum. Across enough systems, the broad rules may begin to emerge. There may never be one model that explains every sky. The solar system has already shown that nearby planets can follow very different paths. Exoplanets widen the range further. Some atmospheres will not fit categories built from Earth, Venus, Mars, or the giant planets. Their chemistry may be expected from known physics, yet arranged in combinations no local world provides. That unfamiliarity is part of what makes them valuable. They test whether planetary science describes planets in general, or only the small collection close to home. They show where familiar climate ideas continue to work. They show where new models are needed, and sometimes they may return the attention gently to Earth. From far away, our planet's atmosphere would also be difficult to interpret. Clouds would hide much of the surface. Seasonal changes would shift the spectrum. Water, oxygen, methane, carbon dioxide, and ozone would appear as narrow features within reflected sunlight. An observer on another world might debate what those gases meant. They might consider oceans, geology, photochemistry, and possible biology. They might remain uncertain for years. Earth would not announce itself to them as a home. It would be a problem in light. That perspective does not reduce the living world around you. It places it within the same physical language used to study every other planet. The air in a room, the water moving through clouds, the oxygen passing through lungs, and the carbon dioxide exchanged by plants are part of a planetary atmosphere, visible in principle across interstellar distance. Close by, these processes feel ordinary. Far away, they would be evidence. The search for alien skies is therefore not only a search outward, it is also a way of seeing atmosphere itself more clearly. Air is not an empty interval between surface and space. It is an active layer where radiation becomes heat, where molecules react, where clouds form, where winds redistribute energy, and where a planet records its relationship with its star. On some worlds, that layer may be thin enough to disappear. On others, it may extend thousands of kilometers above any solid surface. It may shelter oceans. It may conceal them. It may preserve chemical signs of geology or erase them beneath haze. It may contain evidence of life, or only the conditions from which life might one day begin. The light alone cannot promise which answer will come. It can only carry the atmosphere's effects outward. Some of those photons are traveling through space tonight. They left their stars years ago. Before reaching us, a few passed through layers of gas above planets no human eye has seen. Molecules absorbed certain wavelengths. Clouds scattered others. Heat changed the shape of the spectrum. Then the light continued. It crossed the space between systems without losing the small record placed within it. At the end of that journey, a telescope may collect a fraction of it. A detector may count the photons. A line may appear on a graph. Someone may compare that line with models and recognize the possible outline of a distant sky. The planet will remain where it is. Its winds will continue moving. Its clouds will gather or dissolve. Its star will keep shining through them whenever the orbit allows. And here, within that arriving light, another world's air will rest for a moment. The spectrum keeps the sky.